Okay, let's start with MagNet tutorial. Today, I'm gonna walk you through MagNet and different options that you have in MagNet in order to perform an FEA simulation process of a low frequency device. I will use an example of a simple coil to show you how it works from the very initial steps, which is drawing the model and making components, to assigning different mesh sizes and solving the model, and finally extracting the results that you need. So let's open MagNet. We go to MagNet. This is the environment that we have in MagNet. There is a blue area here, which is the main area of MagNet, where you can actually draw the model, the structure of the device that you have, assign components, as I said, observe the mesh structure of the device, which can be a motor, generator, transformer, simple coil, whatever you want in the low frequency domain. Also, once the model is solved, you can actually plot the results here, both the global and local results. And I will explain what I mean by global and local. There's another panel here on your left, the white panel here, where you have a few tabs here. The main tab is the object tab, where you can see the list of the components of the device once it's drawn and implemented here in the blue area. There is the field tab where you can find different quantities, electromagnetic quantities that you can plot afterward once the model is solved. There are counter plots that you can use, for example, be smooth, meaning that you can plot the magnetic flux density, its absolute value, the normal and tangential components of B, X, Y, Z components, and things like that. You can also have shaded plots and arrows. It's not active yet because we don't have any model ready or any results ready here in this tab, so we can discuss more about this once we implement a model, a simple model, and get the results first. I mean, solve the model first. So there's also the Coil Tab, Material Tab. These are the materials which are available in MagNet. These are the same materials that we have in MotorSolve. So they share the same database, so there's no difference. Well, you can also add, like MotorSolve, you can also add user materials in MagNet as well. If you have a material, you need to use a material that is not available here. You find a data sheet from the internet or do the measurements using the setup that we have in the lab, and then import the properties here using this option, user materials. And there are also a few menus here: file, edit, draw, model, boundary condition. Using this tab, you can draw the structure using lines, arcs, and circles. This is actually pretty much what you need to implement the structure of the device. There's also a model tab here where you can create, basically by means of this tab, you can actually extrude the model in the third dimension. What we usually do in magnets or in doing electromagnetic simulation, we first draw a 2D structure of the device, and then if there is no asymmetry in the third dimension, we just extrude that 2D in a line, okay, along the line in the Z direction. So you can also make component in an arc or a multi-sweep component you can also have. So you can make it spheres, cylinder, cones, and many other options you have here. You have boundary conditions. I don't know if you guys familiar with boundary conditions. That this is one of the fundamental concepts of finite element solvers. Let me close the window. I'm sorry. So it's a bit noisy. So
Yeah.
yeah, boundary condition. When when you have a device which is symmetric, even in 2D, not in 3D. For example, you have a motor, 24 pole motor, like the motor that we uh, used in our motor salt model. Let me show you an example here. For example, this motor, right?
Yeah.
Motor has 4 poles, right? So you can easily cut the one pole and just simulate that one single pole, which actually consists of 90 degrees,
Mm,
mechanical degrees, right, of this structure, from this point up to this point. So you can just take this part of the motor and ignore the other 3/4 and simulate that single part, I mean 1/4 in MagNet,
mm,
this environment, which is going to be solved faster than this full model. Because in a full model, you have larger number of meshes and unknowns. Obviously, it's a bigger model, and it will take much longer to solve than one part of the model.
mm.
So once you implement that one single part, 1/4, you need to apply some sort of boundary
Boundary condition.
condition, yeah,
Yeah.
to make sure that the flux distribution is the thing that is the same as what we get here from the full model. So if you are not familiar with boundary conditions and different options that we have, I would highly recommend to read about it, because these are really useful, especially when you want to deal with a large model. You can easily cut it to symmetric components and just simulate that single component.
Yeah.
So you have different options, for example, flux tangential, flux field normal, even periodic, odd periodic. These two can be used in motors and generators.
Mm,
And so also some other options that you have that are used mostly in 3D simulations. We have circuit tab, solve tab. We will go through them one by one once we implement the model. So you also have the scripting tab here, which is really interesting and useful. I will show you how to use the scripting tab that will actually help you to kind of automate the implementation, the entire magnet implementation of any electromagnetic device. So you won't even need to open magnets,
do
draw
everything. Yeah.
draw the structure using the tabs and options that you have here, and then solve the model. You just automate that using MATLAB by connecting magnet to MATLAB or Python.
Yeah.
So in the beginning, there's a couple of important things that we need to preset. For example, you go to the Tools tab, you can set the units.
Mm,
Depending on the dimension of the device that you have, you can set different dimensions and parameters that you have. You can set different units, but we usually use millimeters for length and milliseconds for time, hertz for frequency, and obviously Celsius for temperature. So the only thing that I personally change in the beginning is the length from
mm.
meters to millimeters, because meters is not a good unit for motors and generators, except for there's very high power
Very big.
generators which are like whose dimensions are meters. Let's say that their length is usually about 10 meters and their diameter is about 2, 3 meters. The other types of motors and generators are typically small, so you don't really need meters. It's better to use millimeters. So apply that, go to tools again, and click on keyboard input bar. This is really useful when you want to draw the structure here. As you can see, the unit is automatically changed to millimeters because we already set that to millimeters using the units tab. So here you can enter the coordinates of the lines, arcs, or circles that you want. You have few options here. For example, you can switch from Cartesian to polar coordinate system. You can also enter absolute or relative coordinate systems.
Okay.
So to start off, I'm gonna show you the structure of a simple coil problem that we want to implement together here. This should be 0. Okay, this is the structure. We have a cylindrical airbox as well as a copper coil with the depth of 100 millimeter. The radius of the airbox should be 10 millimeters, and the that of the copper coil should be 2 millimeters. We're going to implement this structure in MagNet and then assign materials. Obviously, here we should assign copper, and for this white region here, we should assign air, and then try to simulate the model. So we have circles, right? And also, like I said earlier, we usually start with implementing the 2D model. You go to Draw tab, or you can simply select the circle here. Go here to the Keyboard tab. As you can see, it's written, specify the center point and the point on the radius of the circle using the mouse or the keyboard bar. Okay, the center would be the origin of the coordinate system. Once you enter that, you can see that you have the option to change the radius by mouse or enter the value, the numerical value in this bar. So let's first deal with airbox. The radius was 10. Now we have 10, a circle with a radius of 10 and the center located on the origin of the coordinate system. Okay, now there's an option here, automatic view all. If you click that, it will automatically fit uh, the structure inside properly inside the window. Next, we're gonna draw the copper coil in the XY plane. So the center is 0 and the radius is 2. This is it. Okay. So you can rotate this structure. As you can see, you can have the 3D illustration here. However, the drawing is still in 2D. We haven't extruded that, so let's have the 2D dimension here, 2D view here. You can change the view as you can see from XY to ZY and whatever option that you have here. After that, so we already drew the airbox and coil. Now, okay, you can also select the lines. There's an option to select the curves and lines here. If you click on this line or arc selection tool, you can select them one by one, and you can see that a circle in MagNet consists of two segments, right? This is the standard of MagNet. It draws the circle using two arcs connected to each other. So you can also select all of them by pressing Control A. Once you do that, or you can also select only one circle here or one segment of a circle here, you can apply some kind of transformations that are available in MagNet. If you go to the Draw tab, under Draw tab you have Scale Edges, Rotate, Mirror, Shift, and for example, let's say we're gonna scale, for example. We're gonna scale the copper coil, which is already selected. We're gonna scale that based on the center point, which is the center of the actual origin of the coordinate system. We're gonna scale that by a factor of 2.
Okay.
Okay, it will double the radius as you can see here. We can apply this actually all the all sort of transformation that are available here. You can shift it, mirror it, rotate it, scale, or apply general transformation. Basically, you can apply scaling, rotation, mirror, shift,
Perfect.
all together at the same time, okay? You can also keep the original copy and just tell the software to create copies of
Copy.
the
Okay.
transformed drawing. So let's go back to the original design, which is this. Now the next step, once you draw uh,
Outline.
the arcs or the structure, you should actually assign components. By assigning components, I mean you select this tool, which is select component face. For example, here we have airbox.
Yeah.
Why is, okay, sorry, this one, surface face. Because we don't have a component yet, we haven't created it yet. So
Yeah.
first we need to create the component. We select the airbox, go to the model tab. Under the model tab, as I said, you have different types of sweeps, line, arc, or multi-sweep. We're gonna deal with an S-straight device, right, in the Z direction. So select the first option, name it airbox. The material obviously should be air, and the length is 100 millimeters. Okay. Again, do the same for the copper. Select the copper surface, make component in line, copper coil, name it copper coil, whatever you want. Select the copper material. This is one of the copper materials that are available, the pretty standard one. The same sweep distance is available here, okay. And now if you select this rotation tool, you can see that we have the 3D structure here. If you select on the airbox, it will select the airbox. The same applies to copper coil or any other component that you add to this device. So as you can see, once you create the component, it will show up here in this tab on your left, right? And it has some properties. For example, phase 1, phase 2. When you, in an optimization process, which is actually the most probably the final goal of using these software packages, I mean MagNet and more as well, you will need to, in MagNet, you will need to take control of these faces or vertices that are available here. If you select this, select and distort component vertices tool, you can see the vertices as well as the faces by selecting different phases under different components. So you can also do the same for the copper coils. So you should kind of control them, their parameters, I mean their dimensions or materials automatically. I'm going to walk you through that later on using MATLAB. But for now, these are the faces that are available. You can also right click on each and every component, go to the properties page where you have you can set the mesh density of each and every component individually. You have the material, you can change the material here. You have the parameters tab, individual parameters tab for each and every component or for the entire model. If you click on MagNet 1, right, this is the name of this model, this whole model. You have the global parameter page, which is here. As I said, each and every component has its own parameter page where you can find the material and the other options that are already set, or you can set in later on. For example, you can set the temperature. If the material properties, for example, copper properties, are available at different temperatures, or the temperature that you want to deal with. For example, if we said 130 degrees, if it's available at this temperature in MagNet, then it will set the properties to that temperature, to that of that to the properties of that temperature. But most of the time, usually what the case is that the material properties is only available at one or two temperature, except for permanent magnets. If you go to permanent magnets, for example, one of the NdFe boron types, under Material tab, you can see that, for example, demagnetization is available at different temperature levels.
Okay.
This only applies to specific types of permanent magnets. If you go to soft magnetic materials, for example, M19, which is not a permanent magnet, let's see, okay. The properties is available at 20 degrees,
20.
and it's only available it's available at 20 degrees, not the other
Okay.
temperatures.
Mm.
So you can measure the properties at different temperatures and input them here. You can change the temperature and then define a new material, apply a new temperature, and enter the corresponding values. It's up to you and your design problem. But in Magnet, we are kind of limited in that sense. So we have created the 3D model here. The next step is to to create coils, right? Any electromagnetic system, at least in low frequency applications, have its own excitation, right? And by excitation, it's usually electric excitation where we have coils. Obviously, we have a copper coil here, so we have already assigned the material, which is copper, but we haven't assigned the excitation. And by that excitation, I mean voltage or currents that will pass through the coil. So you select the copper coil from the Object tab, go to Model.
Mm.
There's an option which says Make Simple Coil, right? We will make the coil, and a new component will be added here. And now if we go to the 2D view, in the XY plane, you can see that the current direction is shown here, right? We didn't have this already. If, if we remove the coil, you can see that we have a solid
Solid.
orange
Yeah.
color here. Once we assign the coil, it will change to this. It means that the coil, the electric excitation has been assigned.
Okay.
Again, if you go to the properties of the coil, you can see that you have many options here. You can have a stranded coil or solid coil. We set it to solid with no strands inside the coil. It can be current driven or voltage driven. We're gonna stick to current driven. You can change the coil side. For now, the current will flow from phase 1 to phase 2. You can reverse the direction to phase 2, from phase 2 to phase 1. Let's see what happens if we do that. Okay. As you can see, this symbol has changed,
Mm.
right? It
Yeah.
didn't have these lines here. It means that we can observe the current direction using that convention of magnet, but we bring it back to the original one. It doesn't really matter. It's up to you. You can apply different waveforms to the coil excitation. One of them is DC, AC, or you can apply sinusoidal, exponential, pulse, piecewise linear, or AC-DC waveforms as current or voltage or whatever you have already assigned here. If it's current driven, it will apply current with the desired waveform specified here. It will apply voltage if you set it to voltage driven. For now, we're going to apply the sinusoidal excitation. And here's the waveform that you can apply. We have V naught, which we will set, which is the DC bias. We set it to 0. VA is the magnitude of the sine. We set it to, let's say, 100 amp. The default values of frequency, the value of frequency is 60 hertz. We can leave it as it is, or we can check this and then apply a new value. For example, 100 hertz. It's up to you and your design problem. And we leave the other parameters to, yeah, as it is. It's okay. So we have the waveform here. We have a sinusoid with a frequency of 100 hertz, magnitude of 100 amps, right? Because it's current, not voltage. So it should be ampere. We also have parameter tabs. Here you can, instead of changing the parameters here, you can change the same parameters here under waveform values in the parameters tab. That's another option to, which makes MagNet very flexible in terms of parameterization. I'll tell you later how to deal with this. For now, let's apply the changes. So we have applied the excitation now. Let's see what's the next step. Okay, select components. Okay. Let's view the 3D. You can also select the surfaces by choosing this tool, select component face, right? You can also select the component, the entire component as well. You can also select vertices. Vertices are really important. And by vertex, I mean this. If you select this tool, it will show all the available vertices of the design. These black dots, if you
Yeah.
click on them, you can, for example, if you click on this vertex, sorry, and move your mouse, you can change the dimension, right? Freely. Can you do this? So this gives us the capability to parameterize the model. So if I click here, it will change the dimension, as you can see. The airbox is kind of asymmetric along the z-axis, right? So using the vertices, we can parameterize the model and change the dimensions automatically. Well, for now, let's go to the next step. We already assigned the excitation.
Yeah.
Once you have modeled the completed structure, here we have a completed structure, right? We haven't used symmetry, we haven't cut off a part of the model or things like that. So once you have the completed structure, most of the time you don't really need to assign boundary condition because the problem will be solved. The solver, the FEA solver, will be able to solve the model as it is. However, if you can also apply the boundary condition if necessary, for example, we know that the current here is in the z direction, right? So based on the right-hand rule, the laws of physics, we know that the flux lines should be parallel and concentric, right, around the origin of the coordinate system. And we expect that the flux values will decrease as we move from the copper coil to the outer surface of the boundary, the airbox, right?
Yeah.
And we know that the flux lines should be kind of circular around this coil, meaning that we have to apply boundary condition to the outer surface of this structure that guarantees that circular waveform. So which boundary condition guarantees this uh, aspect of the device? You select the airbox, I mean the surfaces that we need. What is the surface of boundary condition? We don't need to apply boundary condition on these two ends.
The
However, we have to apply boundary condition
very
on these
flat
two surfaces.
surfaces.
So we select those two surfaces. Now the boundary conditions are active and we can select one of them. So what is flux tangential? You go to help. This help document of MagNet is very useful.
Mm,
You type flux tangential, the first option, flux tangential. Select about the flux tangential boundary condition. You can find the explanation.
ah, okay.
The flux tangential boundary condition constrains to zero the normal component of the magnetic flux density. This is what we need, right? By normal component, it means the component of the flux in the radial direction. We know
Normal to
that the
the
radial
surface.
component should be zero. However, we should have some tangential component in the theta direction, right?
Yeah.
So that's the proper actual boundary condition that we need. So we assign that. You can see that the color has changed. We have some sort of pattern here. And the new component, which is called boundary condition, has been assigned to the model. If you right click, go to properties, you can find the same options here: flux normal, field normal, flux tangential, and some other options. You can also change it from here, but I believe that if we change it to flux normal, since it's not compatible with this model and physics of
Mm,
the model, if we try to solve the model, it will return error because the
mm,
finite element solver will try to create uh, kind of tangential flux values. However, we try to force the values at the boundary to zero. I mean the tangential values, which is not compatible with the physics.
mm,
So we leave it as it is, flux tangential. So which I believe is the correct boundary condition here. However, for this problem, since we have modeled the complete problem, we haven't used any symmetry or stuff like that. Even if you don't assign the boundary condition, I think it will run properly and correctly. We will give it a try. And okay, we have assigned the boundary condition now. Okay. Like I said, every time you don't know anything about the options, tab settings, whatever, you just go to the index, I mean the help document, and search for that keyword, and it will give you the explanation as well as examples on how to implement or use these settings properly. So I think, yeah, the model is ready. We can now solve the model. To solve the model, we have several options. We can solve the model in 2D or 3D. Since there's no rotation or any sort of movement in this device, it's an static device. It's a static device. So we can also use 3D solver, which is not that time consuming for a static device. However, I mean a stationary device. However, if you have a device like motor where you have motion, then you need to run the device using transient with motion analysis
okay.
solver. There, I would recommend to use the 2D solver, not 3D, because 3D will be really time consuming and you will most probably face a lot of errors in terms of meshes, not errors, but warnings, or maybe you need to make some adjustments to the mesh structure, which is kind of tricky. MotorSolve runs the model in 2D, the electromagnetic models. However, the thermal model is run in 3D. In MagNet, you have the option to run in 2D and 3D. It's up to you. What I mean by mesh structure, before selecting a solver or applying different values to the solver options, I would like to show you the mesh structure. If you right click on in this blue area, you can see that you can see this option: initial 2D
Three.
mesh, initial 3D mesh. If you click on the 2D mesh, select the XY plane, you can see the mesh structure, right? I don't know if you're familiar with the finite element solver, but what it does in general is to fit some polynomial functions over these mesh elements
Mm.
and try to find the coefficients of those polynomial functions to that fits the physics of the problem. And by physics, I mean the excitation, boundary condition, and things like that. So there's an iterative solver here which solves the equations of physics over these mesh elements iteratively until it converges to a stable point.
Yeah.
So you can assign different polynomial function or different orders of polynomial functions. It can be the first, second order, third order polynomial functions or things like that that can be set here under Solve tab. If you go to the Solve tab, Set Solver option, uh, yeah, polynomial order, right?
Mm.
You can set it to 1, 2, 3, or 4. 1 and 2 is good enough for our simulation purposes. 3 and 4 is not really needed. If you take a look at the 3D mesh as well, you can see the 3D mesh structure, which is distributed over the device. And you can also change the mesh density. The coarser the mesh, the less accurate your results would be.
Mm.
This is kind of a very coarse mesh. I don't really like it. You can assign a global mesh density if you go to the Object tab, right click on the global model, go to the properties. Under the Mesh tab, you can set the maximum element size to, let's say, 3 millimeters. Apply. It's a still coarse, 1 millimeter. It's getting refined. Okay. 0.2 millimeters. It's a very refined mesh.
Mm.
If you do this using the global model properties, it will apply this mesh density to all the components in your model. However, you can change it separately for each and every model. We go to the airbox, change the mesh density of the airbox to, let's say, 3 millimeters. As you can see, now we have a coarse mesh for the airbox and the refined mesh for the copper, right?
Yeah.
Do the same for copper. 0.2 is too refined. We don't really need that. 0.5
Five.
is a good one. This is a very simple problem. You don't really need that refined mesh. So this is what I mean by mesh. You have some other options as well. For example, curvature refinement, minimum element size. Sometimes you will get some, once you run the model, you will get some errors in terms of mesh structure of that is used for solving the model. In that case, if you face that kind of problems, you need to change the curvature refinement and these parameters which are available here and under the mesh tab, and play with the values until you get a stable result. But most of the time, it's not really required. That's about it. And now I think the model is ready to solve. But
Mm.
let's go to the solver options first. As I said, you can change the solver actually parameters. For Newton-Raphson iterations, you can have the maximum number, polynomial order, as we explained earlier, source frequency, this has to be set to 100 because the excitation was 100, right? Don't forget that. You also have the CG, conjugate gradient tolerance, which this conjugate gradient solves the system of equations that is obtained from this final assembled finite element structure. The Newton-Raphson iterations is used to deal with the nonlinearity of the material. However, we don't have any nonlinear magnetic material here. It's just copper and air. These are not nonlinear. But if we change, for example, the air to something like M19, which is a nonlinear ferromagnetic material, then Newton-Raphson iteration will be applied. You can also change the material type to linear or nonlinear, but set it to default all the time. The problem will actually, the solver will recognize the appropriate solver itself. In 2D simulations, only Newton-Raphson solver is available, which is stable and fast enough. In 3D, MagNet only uses successive substitution. So this is the solver option. Okay, go to the transient options. We have, as if you remember, as excitation, we have a sinusoid, right? Which is in time domain, it's a transient signal. It's not DC, right?
Yeah.
So we need to set transient options here. If you click on transient option, this window will pop up. Set the start time to 0, the stop time. We're gonna simulate the model, for one cycle of that sinusoid. The frequency was 100 hertz. So the period would be 1 over 100. And this step, as you wish. Set it to, for example, this one, or maybe smaller step. We don't need power loss here for now. Let's apply the changes. Now it's ready. I hope everything's fine. We will find out. You can have a static 2D solver. This solver, try to use it when the excitation is DC, because it's just one snapshot of your device.
Yeah.
And static 2D, if you use it here, I think it's just gonna take the first time instant of the sinusoid that we applied, that we defined. Okay, what's the problem here? The sinusoid has changed. So you should double check the waveform. We changed the transient option, now it has changed. So why is that? Let's check it out. So this is milliseconds. So let's see, increase this to 5 and see what happens. Yeah, every time you run the models, just double check what you are doing. But I think here the excitation, okay, 100 hertz. There's something wrong with the units. Millisecond. Okay, here we also had milliseconds, right?
Yeah.
Okay, sorry. I've entered that in seconds. So,
okay.
right. So, let's make it second, for example. We apply that, and for seconds, okay. Okay. And now let's get back to the waveform. Okay, now we need the sinusoid. Okay. Transient 2D is what we need here, right? We can also try 3D. For now, let's try 2D and solve the model. And it's running, so it's good. The model is solved. Let's go back to the solid model. Once it's solved, it takes you to the results tab, as you can see here. Under the results tab, you can find the energy, forces, flux linkage, ohmic loss, iron loss if you have ferromagnetic material, which we don't, current, voltage, temperature. The input was current, right? Because it's a current-driven model. You click on this value, graph selection, it will give you the same sinusoid that we assigned to the model, right? If you go to the voltage, it will give you the voltage induced across the copper coil. The voltage is very small, as you can see here, the amplitude, because the resistivity of the coil, the copper coil, is very small.
Very high. Small.
So ohmic loss, this is the ohmic loss of the copper coil. Flux linkage is also available across the coil. Forces, we don't have any force. Why? Because we don't have any rotating or moving component. So force or torque doesn't mean anything here. However, the value is very small, negligible. It's very negligible because of the numerical round of errors. Energy is also available. So that was the result tab.
Okay.
That you could access from here. You can also go to this panel, select the field tab, and plot whatever you want here. So for example, be a smooth, at which time instant, any time instant that you want. For example, 6 milliseconds. Update view, it will give you the flux distribution, right? This is the flux distribution that we get from the model. You can change it to, I don't know, time average ohmic losses, right? This is the counter plot. Okay, the shaded plot, time average ohmic losses. This is what you get. Obviously, the ohmic loss in the airbox should be 0 because there's no resistivity in the airbox. That of the copper is the maximum, and here's the numerical value on your right. And you can also have arrow plots. For example, B. This is the direction of B. And once you run the model using the transient solver, and you can animate all the time instance. Let's do it. It does the animation, so you can have a better idea of all the time instance. However, it's going to take a while. I'm going to stop it by pressing escape. So you can change the time instant to, let's say, the last one, 10 milliseconds. This is what we get. Let's get back to B. This is B a smooth. By a smooth, it means that actually MagNet does some sort of apply some sort of smoothing function. However, the original B values are this, which are not smooth. So it does the smoothification by itself. And yeah, if we change the time instant to, let's say this, we can see the difference in the numerical values over the plotted quantity. So this is how we get from modeling, I mean drawing the model, assigning the components and things like that, to the final step, which is solving the model and plotting the results in the MagNet user interface, not in an automated way, which is done by MATLAB, for example. As I said, we can also have a 3D finite element solve here. Let's run it just for once and see what happens to the model. Here we can only, if we run it in 2D, we can only get the results obviously in 2D. In 3D, it's gonna take a while, but it's solving. As you see, there is no Newton-Raphson iteration here. It's not active because we don't have any nonlinear material.
Okay.
However, CG, conjugate gradient,
Gradient.
is running to solve the finite element matrices in order to get the final result. As you see, it's getting closer to the minimum error. Okay, now it's running for different time steps. It's taking too while. Let's see. Okay, this is good. You can control the speed accuracy trade-off of this simulation process by one, changing the mesh density. The coarser the mesh, the faster the solver, okay? Also, you can change the error of the CG and the Newton-Raphson, the tolerance, I mean. If you increase the tolerance, obviously it will solve in a smaller number of steps. However, the results wouldn't be reliable enough. Let's see what else we can do to change the speed of the process. So one of them is mesh density, the solver. This is good enough, I guess. So it's going to take a while. Let's change the adjustments a little bit. Let's change the number of steps. Transient option, instead of 0.1, let's apply, I don't know, 2 milliseconds. And increase the mesh size from 0.5 to 3. And use the 3D solver again. Okay. Now in 3D, you can get the 3D view of the solver. If you make the airbox invisible by right-clicking on the airbox and doing this, you can see this surface field values around the copper coil as well, right? So you can activate or deactivate the components and see what's happening inside each component. Okay. That's about solving the model. Any questions so far?
Okay. Usually, do you export the model from somewhere else, or do you make it in MagNet?
What I
Import,
did in
sorry.
my, okay, what I did in my PhD
Yeah.
was to use magnets all the time. I implemented the model from scratch, a model of an IP motor. I'm going to show you the model and the process that I used later on, maybe at the end of this tutorial. Yes, I'm a fan of magnet. If you really know what you are doing, magnet is the best because it gives you more flexibility in terms of the adjustments. In terms of motor sub, you don't really know what's happening in the background, right? So you just rely on the settings of MotorSolve. But as I said, if you really know what you are doing, then MagNet is the better option.
Yeah. It's more flexible.
Yeah. So because honestly, in MotorSolve, you don't, for example, you don't really have access to, for example, edge values, or maybe you do. I'm not sure. I haven't used that. But the quantities that you have here in MagNet would be really useful. Also, MagNet has some capabilities called field extractor, field integrator. Okay, let's discuss them first. These are very useful. Uh, Once you solve the model, let's solve it in 2D again. And let's change the mesh density of the airbox to get a better solution. Let's change that of the copper coil as well to get some refined solution and run it in 2D. Okay. And at this time instant, update the view. This is the better representation, right? So once you solve the model, if you go to the extensions tab, field extractor, it will open up a new window where you can extract B values, local value. Okay, by local values or quantities, I mean, for example, something like B. The values that are distributed over the mesh structure, right? However, by global quantities, whenever we talk of global quantities, I mean the quantities in the results tab, where you don't deal with mesh structure or the field distribution over the mesh or over the device cross section. So we go back to the field extractor, select, for example, magnitude of B, and we want to find the magnitude of B along a line, for example, a line which is located, for example, here on the x-axis, right? From the center point to the last point of the device, which is somewhere here. We can actually use Cartesian or polar system. Let's use, for example, the first option. Add the coordinate, the first coordinate. We're gonna start from 0 up to the last point of this device, which was, if I'm not wrong, 10 millimeters, right? The outer radius of the airbox. We're gonna extract 100, the V values over 100 samples, or you can make it 200 samples, whatever you want. And the Y coordinate will be just 0 and 1 value. You can extract the out and extract and output the file. Okay, at which time instant? Let's select this time instant, or this one, the fourth one. Click extract. It will give you the numerical values of the quantity that you selected, which is magnitude of B over that line, right?
200 samples over that line.
Exactly.
Yeah.
200 samples, right? So, or you can just graph it or plot the graph here. This is the field distribution, the distribution of magnitude of flux density over that line. You can select another quantity. You can change your sweep and do the extraction for all the time instants. Let's graph that. Okay, as you can see, we have the B value at all the time instance, right?
Mm.
So this is a very useful capability of MagNet. There's also another option that you have, field integrator. For example, if you need to integrate, for example, B values to compute the flux in Weber. We know that flux in Weber is the integration of B over a surface, right?
Mm.
So you can add the quantity, for example, B here, you can select the component here and do that integration to get the flux values, magnetic flux values in Weber. So these are very useful. You might be needing to use these in future. So that's about the field or the result extraction. You can also, once you create the coil, go to the circuit tab, create new circuit. And by the new circuit, I mean this. That code that you have created is available here. You just drag it and drop it here in this window. Also, you have several options too. You can assign, for example, instead of assigning a current here to the coil, you can use the current source here. Drag and drop, or just click on this current source. It's not a user-friendly
Mm.
tool. It's very simple and fun, basic, but you can use it anyway. You can also add a resistor, capacitor, inductor, switch, diode. For example, if you want to implement an inverter, you have, for example, you have a motor with 3 coils connected, for example, in Y connection. You can add 6 switches, diodes, and things like that to implement an inverter here. This is something that can be used for to implement electric circuits with electric components. But for now, we're gonna ignore that because we have already assigned the excitation that we need. You can change the excitation, as I said, to DC, AC, or if you have PWM excitation from somewhere, for example, from your experimental setup, you just choose piecewise linear, add that waveform as a piecewise linear waveform here. For example, at the first time instant, at 0 second, we apply 100 amp. At 1 second, we apply, I don't know, 0, something like that. Piecewise linear waveform you can easily apply.
Mm.
This is another option that you have. But what MotorSolve does is mainly applying this. Basically, MagNet is running in the background of MotorSolve, and what it does is to apply a sinusoidal excitation or a piecewise linear if you have a PWM excitation. Okay, that's about the result extraction. The next step, which is very important, is parameterization and can be used in optimization routines. What I mean by parameterization, there are, let's close the tabs because we don't really need that now. Oops. Okay, let's go to the solid model, 2D view. And for now, let's remove the boundary condition. Okay, select the vertices one by one. For example, this vertex, right, which is here. Go to the properties. As you can see, under the properties tab, you can change or parameterize the position of that vertex, right? This is one way to parameterize the model. How? click on MagNet or the Properties, the Parameters tab of the global model. Define a new parameter, numerical, for example, numerical parameter. For example, airbox radius. We set it to, it's already 10 millimeters, right? So we set it to, for example, 20. And we want it to be in millimeters. This is the convention that we use in MagNet. If you want to change it to millimeter under parameters tab, because the parameters tab only works with SI units, as you can see here. Default units are SI, right? So it's meter. So to change it to millimeter, you just add a percentage sign and type mm, millimeter. Also, we want to change the radius of, or parameterize the radius of the copper coil. Copper coil radius. It was 2 millimeters, if I'm not wrong. We make it, for example, 5 millimeter. So we define these two parameters here, apply, then go and select one of the vertices, for example, this one, go to the properties. Here, you should enter an array. What is the position? The position is X, Y, Z, or in 2D, only XY of that XY coordinate of that selected vertex. That vertex, I mean this one, is located on the negative side of x-axis. So this is how we use the two parameters, or the parameters that are defined in the Parameters tab of the global model. Airbox radius. So using, again, this percentage sign is basically adds a reference, basically refers, using that we can refer to the parameter that is already defined. And the y coordinate of this vertex is 0 because it's located on the x-axis, right?
X-axis.
So apply. Now, as you can see, the change has been applied, right? That vertex has been moved to the desired location, new location. Now select the other vertex. I'm gonna do this one by one and walk you through that just for this simple example to show you how it's done practically. You should do it for all the vertices that you want to parameterize. Again, negative percentage, airbox radius, and 0. We can copy this. Okay. Paste. Apply. The airbox has been parameterized. As you can see, these green lines and arcs are still there. That's called wireframe model. Those green lines, okay? Oh, why is that? Sorry, let's bring it back to the parameterized value. That green line shows the base design or base drawing that we had. So in order to avoid confusion, you can just remove it. Okay. Now we have the airbox parameterized. Go back to the solid model. And if, just look at this, if we change this 20 millimeter to, I don't know, 50, apply, it applies the change automatically, right? Let's bring it back to a value around, I don't know, 13, whatever we want. Now let's do the same for the copper coil. negative percentage copper coil radius 0, copy, apply, select this vertex, copy, apply, apply, and one more vertex.
Yeah.
It's this one. Okay, the whole model is parameterized now, right?
Yeah.
So again, if we change this to 10, for example, or whatever you want, it will apply the changes. You didn't really need to remove the boundary condition. I did that to make sure that the vertices are visible. You can actually reassign the boundary condition. Let's go to airbox, select the surfaces that we need, assign the boundary condition again. Save the model somewhere, for example, here, and let's name it coil. Or is it already there? Let's see. No. Okay, the extension is MN, MagNet. So the model is here. It's ready. Close the model, open the model. And now I'm going to show you how to use this parameterized model and control it using MATLAB automatically. Let's solve the model once to make sure that the model works. Yes, it works. Let's check the 2D mesh structure. We can refine the model a little bit. I mean the mesh structure. Okay, since we have already assigned it. Okay, now it's refined. Save, run. It's solved. Let's double check the field values. Okay, good. This is the base model. So this is the base model that we have. Now we open, I've already written a code in MATLAB which shows you how to control or call the magnet session from MATLAB and then do the adjustments, run the simulation and extract results. So here's the code. Guys, any questions so far?
No.
Good. So let's go through the code line by line. Okay, reset magnet session. We're gonna reset magnet session. If you can use this function, system, which is a MATLAB function, task kill, any magnet session which is open will be killed, okay, will be closed. Okay, if you go to the start task, go to the task manager, you will see that there's no magnet session here, right? So you can do the same for motor solve as well. You can type here motor solve or termnet, whatever. Now we're gonna create a COM server in order to open magnet session. This is the function that you use, ActiveX server. Now the COM server has been created, and now you can open the created server or the magnet session. If you set the visibility option to true, run the code, it will open the magnet, a magnet file, right? So, however, let's close this and make this, change it to false, run the code. The session has been created. However, you cannot see the magnets, the open magnets session, right?
It's just running in the background.
That's correct. It's running in the background. This is this approach. I mean, making the visibility, changing it to false, is very useful when you want to run several hundreds or thousands of models and you want to make the process faster. Because to be honest, opening up the user interface and basically illustrating those solver operations and stuff like that will take time. So just once you make sure that the model is working fine, just run it in the background. You don't really need to visually see what's happening inside the code. I mean the MagNet model. So there's a couple of other options that, I mean, lines of code that you need to execute to make sure that the model is ready. I mean, the magnet's environment is ready. And these are these are basically defaults, and you can just copy and paste these values. It will get the magnet constants, open a new document, get the view, and then using this line of code. Okay, let me show you what it does. You can control the resolution or the position of the magnet in user interface on your screen. Let's run that line of code. You can see that the magnet is kind of moved to the right side. You can change the resolution from 860 to whatever you want. You don't want, but actually you don't really need this. This is just something that you can use to make the visualization better. So let's run up to this point again. And since we have already created the model, let's bring it back to this side. We can open the magnet model by using the invoke function of MATLAB, calling the magnet, which is defined here, mn, as a com server. You should always use process command and then use this line of code, call open document, and then call the model that you have already created, which is coil.mn, right? This is the VBA script that you can extract from here as well. If you go to the scripting tab of MagNet, you can start recording your script, save it somewhere, and now go to open, click on this. It will record the VBA script of whatever you are doing inside the magnet environment. Now stop recording, yes, it will give you the script, the same line of code, right? You can just copy this code inside the invoke function of MATLAB, like what I did here, and then you are good to go. It will do the same job that you are doing here manually. So let's do it again up to line 21. Okay, now the model is open, right? Okay, by parameterization and optimization, what we do in general, I mean, we generate some samples. For example, the samples here would be the same coil and airbox structure, but with different dimensions. We're gonna create, for example, a few number of samples. We're gonna change randomly the dimension of the coil as well as the airbox to get the same structure with different dimensions, solve every single sample, get the results, and then monitor, for example, the flux linkage value. And for example, again, as an objective of the design optimization problem, find the design or the sample that gives us the maximum flux linkage possible. So this this process is actually starts with generating samples. I mean those random samples. We usually generate random samples using the rand function in MATLAB. On line 29, you can see the random function here, right? Random number generation function of MATLAB. The initial number of samples, let me bring it or minimize this. The initial number of samples that we request is, for example, 10. You can assign whatever you want. However, not all the designs would be feasible. Since we generate the dimensions of the copper radius, copper and the airbox randomly, it is likely that the copper radius becomes larger than that of the airbox, right? Which is physically infeasible. Yeah. So we have to filter out those samples. And that step is called constraint handling. These 4 lines of code for this simple structure. We only have one constraint. We find the copper radius values that are greater than or equal to the airbox radius. We find them and then filter them out from the design space or the sample space. You can also assign minimum or maximum value for the random function generator, or for basically for the parameters that you have. You remember that we already assigned the 2 parameters here in under the parameters tab of the model. So those are the 2 parameters that you can control using MATLAB. You're gonna refer to these parameters in MATLAB using the same exact names. If you enter in MATLAB another name, it won't be able to recognize the name and it will return an error. So I'm going to show you how to do that. For copper radius, we say, for example, we want the copper radius to vary from 3 millimeters to, I don't know, 70, 75. So this function will generate random samples, 10 random samples within this range. The same applies to airbox radius. Let's say, for example, from 10 millimeters to 100, whatever you want. This is the design space that you control. It's up to you. Again, it will generate 10 samples within this range, which will be later on assigned to the airbox. We filter out the designs, the infeasible designs, using these 3 lines of code. If you have a more complex structure, the constraint handling will be, of course, more complex. Let's run the code over from the beginning up to this point. Okay. Oh, sorry, the breakpoint is here. We had to run it up to the... Look at the MagNet, the command window of MATLAB. Number of initial samples was 10. However, the number of feasible samples is 8. 2 samples are filtered out. Yeah. They are infeasible samples, I mean those 2 samples. And we don't care about them because they are physically infeasible. Now we go to the next line of code, which is a for loop. By means of this for loop, we're gonna apply those samples one by one, the numerical values of those samples, to this MagNet model. Actually, we're gonna assign the parameters, run the model, and then extract some results. And in this case, I have the example of a flux linkage. So how is it done? In the next line, we will see that we have the same syntax: invoke, MagNet model, process command, call, get document, begin ungroup, set properties true. I'm going to show you where I found this line of code. And also the next line, the same syntax up to this point. And then we're gonna set parameter. Which parameter? Copper radius, which we already defined in the model. And what's the value? The first value of the copper radius, which is generated in MATLAB. If we go to the workspace of MATLAB, copper radius, there should be 8 values, right? Because 2 of them are filtered out.
Yeah.
It's gonna take the first value of the copper radius, as well as the first value of the airbox radius, and apply these 2 values to this parameters tab. How is it done? By means of this function, set parameter. It will change the parameters in the global model parameters tab, like in this page. Whatever parameter you define here can be accessed using the same syntax in MATLAB. So if we run the code, it will run it line by line. Okay. If we go back to the model, you can see that the model has been changed. If we go to the parameters tab, okay. Now I made some wrong changes here because of the names. Okay, copper radius. It didn't assign, okay. I entered the names wrong. Copper coil, copper, okay. Okay, this should be copper coil, right? That was wrong. So actually good to know. If you enter a wrong name of the parameter, it will create the new parameter here, and which is useless, totally useless. We don't really need this. Just remove it. Okay. But the rest should be fine. Let's run the code up to this point. Nice. This is the new model. Go to the parameters tab. Okay, now these are the numerical values. Airbox radius 97, the same as what we have here, 97. And the copper radius, 68 point something, 68 point something, right? So the parameters have been applied. Now to see what happens to the other the coil structure. Let's turn off these lines of code. Okay. And run the for loop without solving the models so that you can see what will happen to the model. Look at the models. You saw the change. Let's add a pause here for 1 second. In between each model. See? Right? This is how we do parameterization using MATLAB. And the same procedure of running and extracting results can be applied to each and every samples that we generated already. And to extract these lines of code, how to know what to do, or what to put in the MATLAB code. Again, you go to the MagNet environment. Start recording your script. Make the parameter changes. Change whatever you want. Example 20. Okay. Stop recording. This will give you the code, right? This will give you the changes, the code related to the changes that have been made to the MagNet model. Set parameter, we change the airbox radius to 20, and you just copy this line of code into the MATLAB environment and use that later on. The same applies to running the model and extracting results. I will send you the code after our tutorial so you can go through the code line by line and understand what's happening. You can change the solver type from transient 2D to static 2D, time harmonic, whatever you want. Also, you can extract results from the global results tab. As you can see, get global solution time instance. And from that tab, you can extract the flux linkage through coil. It will give you this value. Let's run the model. And by flux linkage, now it's running the model. I mean, under the results tab, the flux linkage. Here we have this waveform. We should be getting the same exact waveform in MATLAB if we do the implementations right. So let's run that for the first sample, for the first loop of, for the first iteration of the for loop. What it does is to run the model, extract the numerical values. Okay, there's an error here. Which line is not working fine? Let's see. Okay, the coil is coil 2. That's the first thing to correct. And let's run the model again. Okay, yeah, it's running for all the samples now. Can you see this? Okay, good. The flux linkage. For the last sample that we have here, if we plot that in MATLAB, this is the flux linkage of the last sample, I mean the 8th sample. And the model which is open is the same exact model, which is the last sample. We go to the flux linkage tab, graph result. This is what we get from MagNet, and the same waveform we have here in MATLAB with the same numerical values. So this is the way you can control the MagNet model. And as I said, it can be run in an invisible mode by just setting the visibility to false. Any questions so far? Okay. This is the way we do the scripting using MATLAB. Now I'm going to give you an example of a more complex structure that actually I use in my PhD. That's the example of an IPM motor. Let's close this, go back to IPM, run the model, and by means of this example, I'm going to explain how to run the MATLAB sessions in parallel using the PowerPool tool and Power4 tool of MATLAB. So for now, let's deactivate this line and run the models sequentially. I've already generated samples of the IPM motor that I'm going to talk about. Here we have 3,000 samples, as you can see. I'm going to run the model for the first sample, And you can see how the parameterization and result extracting is done for this complex model, rather complex model. Okay, this is the IPA motor. Now it's running, but I hope you notice that the model was created from scratch. What I did here in this case wasn't creating the base model beforehand and then calling it from using MATLAB. What I'm doing is basically do the entire process from scratch using MATLAB. Even drawing the lines, arcs, and everything, assigning the model, and every single step that I explained earlier can be handled using MATLAB and the codes that we have here.
You just started recording and made it in MagNet and then copied all the code here.
Exactly, that's the point. I'm gonna send you this code as well, the code for the IP motor, so you can understand how the implementation can be done from scratch using MATLAB. It's pretty straightforward. As you can see, I'm using the new line, new arc, or some functions or something like that. So also, I've only modeled 1/4, 1/4 of the motor, right? Because it's a four-pole machine, you don't really need to model the entire machine, and I've already assigned the appropriate boundary condition. So in addition to the boundary condition, components, and circuit, I also have the motion component, because this is a non-stationary and rotating device where you need to assign the motion component. It's a velocity-driven model where we assign the velocity. Also, you can find the results of the motion analysis here in terms of the load torque, the speed, and everything that is relevant to the motion component. In terms of excitation, in addition to actually, we can have multiple coils here. This is a three-phase machine. You can see that we have phase A, phase B, and C. You may ask why the excitation is set to 0, because in this code, in this line of code, let's see, I'm trying to extract the back EMF and permanent magnet flux linkage. And to extract those two quantities, the excitation should be 0, the excitation of the three-phase winding. So by means of which we can extract the back EMF values in time and frequency domain. I've also done some Fourier transform here in this, let's see where it is. Okay, FFT, fast Fourier transform here to extract the harmonic components of the back EMF as well. I'm going to send the code to you guys so you can take a look and learn how it's done. So in terms of the harmonic components of the back EMF obtained from that model, here's the harmonic components. The first one, which is the largest one, is about 70 volts. And as we move toward the higher values, higher frequency components, you can see that we have variations of the amplitude of the harmonic components. This is the second method of implementing the parameterization. By that, I mean you can basically implement the model from scratch using MATLAB and do the entire process automatically. Now let's get back to the parallelization of the model. Just using this, actually you can just use these 3 lines of code to call the power pool function of the MATLAB, where you can deploy the MATLAB or motor submodels on the CPUs on multiple cores. We're gonna use only 2 cores of the CPU, because if I'm not wrong, we can only access, yes, 2 solvers at a time, right? this is our limit. If the license gives us the capability of using more solvers, concurrent solvers at the time, obviously we can increase this number to 3, 4, or whatever that can be managed by your CPU. Here I have 8 threads, so I won't recommend using all the threads at the same time, because as you increase the number of concurrent solvers, it will get slower. I mean, the entire simulation process. So 3, 4 on this 3, 4 simulations at the same time on this 8-thread machine or 4-core machine is the appropriate value. But for now, we are limited to 2. And instead of for loop, we're going to use for loop, parallel for loop. And we're gonna run the model, and you will see what will happen if we run the model in parallel. Also, let me deactivate this line, which is already done, and let's run the model again. As you can see in the command window of MATLAB, it's starting the power pool, and it will assign 2 CPU cores to this task. Once it's done, it's going to distribute the functions, I mean the models on the CPUs. Yeah, can you see this? 2 models are running in parallel. Now they are solving, and once each model is run, it will extract the results, and you can save the results anywhere you want on your hard drive. So yeah, it closes the solved model and opens a new model. The process continues, well, up to the point that all the samples are run, simulated, and the corresponding results are extracted. Any questions, guys? Okay. Yeah, this is how it's done. Let me also show you the scripting hierarchy of MagNet. You go to the help topics, contents. Under scripting, you can find the scripting hierarchy, which is very important and useful. This is all you need in terms of scripting, all you need to know. Okay, you can go, for example, to the Field tab, and you can access all the functions available in MagNet to deal with the field values, mesh structure, nodes, and everything. Or you can go back to, I don't know, circuit. These are the functions that you can use to deal with the circuit components in your model and things like that. In terms of viewing the results, problem implementation, assigning materials, components, and everything. So let me check my to-do list and see if I've explained everything that you need to know. Okay. I think that's it. So yeah, we are done for now. If you have any questions, please let me know. I'll try to answer if there's any. Otherwise, I can stop recording and send you guys the video.
So for this motor that you were using,
yeah,
when you were parameterizing it, were you just you open one model, change something in that, and then
close the model and
then
recreate the new model.
recreate from scratch a new one.
Exactly. Yeah.
Okay. You're not changing, not opening one window and just changing
No.
it and then resimulating.
No. That's the first method that we use.
Yeah, for the coil, right? That's
yes, exactly. Yeah. Actually, the first method would be faster.
Yeah.
Because you already have the base model.
Yeah.
But the second method is also one way to go.
Okay. Okay.
Yeah.
Mm.
I have a question.
Yeah.
Right. So this is with regards to MagNet and MotorSolve present as a remote software in a computer in the lab, right?
Right.
So if suppose we have to, let's say, access the remote computer and simulate the files that or the designs that we need to, do we save the files in our computer first and then run the MATLAB code, or is it possible to save the file in the remote computer and continue the MATLAB simulation in the remote computer?
Yes, 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 you can do that. Yeah.
Okay. All right.
Yes, you can do that. But you obviously you need to access the remote computer first.
Okay. All right.
Yeah. So what else, guys? So yeah, I think that's it. Thank you very much for your time.
Thank
I
you.
hope this tutorial will be useful for you.
Yeah.
So I'm gonna try sharing the video recording with you. So I'm gonna do that in an hour or so, so you can access today's tutorial as well as the
Okay.
previous one. So thank you very much.
Thank you, Vahid.
Thank you
No
so
problem.
much, Vahid.
No
Thank you.
problem. My pleasure. So just don't hesitate to ask me any question later if you have any.
Okay.
Absolutely.
Yeah.
Okay, thanks a lot. Have a good day.
Thanks, right?
Bye-bye.
Yeah.
Bye.
Vahid?
Yeah.
Okay, so this is with regards to the thesis that I'm currently undergoing. So there's this model that I wish to create based on wind data. So you know that my project is based on wind turbines, right?